Hello everybody, and welcome to this video about finding the antiderivatives of composite functions. Specifically, we'll be looking at doing that by undoing the steps of the chain rule. Okay, so for that reason, I like to call this the anti-chain rule. Once again, this is not an official mathematical term, but I think it aptly describes what it does. Special credit and thanks go to Larry Forrester, from whom I adapted this way of explaining how to do these antiderivatives. Alright, well, let's break some chains, shall we? Alright, first things first. How do we use the anti-chain rule? So we already mentioned that it's undoing the steps of the chain rule, so let's recap what the chain rule is. The chain rule we apply for derivatives where we have a function inside of a function. That's a composite function. Okay? And we had to recognize the outside and inside functions, which earlier in the year, chances are I've used the analogy of an M&M, where the outside of the function is the candy shell and the inside function is the chocolate. And occasionally we have something inside of that, which would be like a peanut. Okay? So the steps of the chain rule were that we take the derivative of the outside candy shell, okay, the outside function, but keep the inside of it the same. Then we multiply by the derivative of the inside function. Okay, so for the anti-chain rule, we need to reverse that process, okay, starting with the last step of the chain rule. So instead of multiplying by the derivative of the inside function, I'm going to divide by the derivative of the inside. Okay? Then, instead of taking the derivative of the outside, we'll do the antiderivative of the outside, still keeping the inside the same. Okay? So another special requirement here is that dividing by the derivative of the inside must cancel out anything else on the outside of the outside function. And that's what I mean by outside components here, besides possibly leaving a constant out front. If it doesn't cancel everything else, then we have to choose a different method. Okay? So more about how to recognize that when we get to the second example. Another final note is that some textbooks will refer to this as U substitution. That is the formal method for how to do the antiderivatives of these kinds of functions. It's the same steps, just framed a little differently. Okay, basically, and more on this in class, the letter U is used as a replacement for the inside function. Okay, so you can recognize what that U is. But again, more on that in class. Okay, so let's jump into an example. Let's start with a really simple example so you can get the idea of what I'm talking about. In each of these examples, we're going to be evaluating the integral, and I can see in this first example that it's an indefinite integral without bounds, which means my answer is going to be a function plus c. Okay? I'll put the steps to the anti-chain rule up here in the corner for our reference. Okay? And just as with the chain rule, our most important first task is to identify what the outside function is and what the inside function is, for which I'll be using the colors red and brown in this video to kind of like a red M&M. Okay, so what do you think? What is the outside function in this case, and what is the inside function when we look at e to the 2x? Okay, well, were you thinking of 2x as the inside function? Okay. So that 2x is inside the e to the something, so well, what's on the outside but e to the something. Then the 2x is inside that exponential equation. Okay, so now then we can follow the steps. I need to divide by the derivative of the inside. So what is the derivative of 2x? That would be 2. So I need to divide by 2. And I'll bring that in front as 1/2. Dividing by 2 is the same as multiplying by 1/2. So that'll be out in front of the antiderivative. Okay, what is the antiderivative of e to the stuff? Well, it's just e to the stuff. So, and notice I kept the inside the same. Alright, so because e to stuff is its own antiderivative, there we go. Except plus c. Don't forget that. Alright, and that's it. This is a very short example, but it's generally a good idea in each of these cases to check, by actually taking the derivative and see if you get the original function back. With simple ones, you can often do this in your head. So if I take the derivative of 1/2 e to the 2x, the 1/2 would stay along for the ride, and e to the power of stuff has a derivative of e to the power of stuff, but I must apply the chain rule, so times derivative of the stuff. Okay, that would be times 2 in this case. 2 and the 1/2 would cancel, and we have just e to the 2x. So really another way to look at it is the 1/2 we stuck out front is what has to be there in order to cancel the 2 that's gonna appear because of the chain rule if I were to take the derivative of that. Okay, so let's look at another example. Here's one that's slightly more complex. Okay, so I still notice this is an indefinite integral, so we'll have a function plus c as the answer. First step, we need to determine what's the inside function and what's the outside function that's it's inside of. All right, I'll give you a few seconds to think about that. Which is the inside and outside functions here? All right, the inside function is the 1 minus x squared. Okay, and what is it inside? It's inside the square root. That's the outside function. But what about this 5x out here? That might have confused some of y'all. Well, those were some of those other outside components that I was referring to earlier that will need to cancel all except for maybe a constant if this is going to work. Alright, so I need to divide by the derivative of the inside. What is the derivative of the inside function? That would be negative 2x. Okay, so let's divide by that. And if you notice, the x's cancel. That's a good thing. Otherwise, we couldn't use the anti-chain rule. Then I can pull the 5 over negative 2 as a negative 5/2 as a constant out in front of my antiderivative. And the only thing I'm allowed to pull in front of the antiderivative is a constant. So if those x's had not canceled and and there was like an x remaining or something else remaining, then I couldn't use the anti-chain rule. And the only thing that must be left outside is a constant. Right. Now I need to do the antiderivative of the square root. How do we do that? Well, it might be helpful to remember that the square root is really stuff to the power of 1/2. How do I do an antiderivative of stuff to the 1/2? Well, I increase the power by 1, so now I'm at 3/2, and then I'll need to divide by the new power, or in this case, multiply by its reciprocal, so multiply by 2/3. Alright, the inside needs to stay the same, and plus c. That would be a safe stop where we are, but if it was a multiple choice question and we wanted to get to the simplified form, then the important thing to recognize would just be that, oh, those two 2's are going to cancel there, and so I have negative 5/3 as my coefficient, and there we go. Alright, let's check it just to make sure that it works. So we'll do the derivative. Okay. We'll need to use the chain rule here, otherwise why would we have undone it? Anyway, so let's do derivative of the outside. So we multiply the 3/2 towards the front, okay, and decrease the power by 1. Inside stays the same. And then I need to apply the chain rule. So I need to multiply by the derivative of the inside, which is negative 2x. Yeah. And then the 3's cancel, 2's cancel, negative cancels, and we have 5x times the square root of 1 minus x squared. Alright, it worked. Alright, let's have one more example. I've pulled in this last example because it has a lot of facets that a lot of people tend to overlook. And really, the first thing that a lot of people start to freak out about is this e plus 5 as a bound. Oh my gosh, what are we going to do with that? That looks complicated. Well, whenever you see a complicated bound like that, that's actually the AP test saying, here, I've given you something that's going to make your life easier down the road, and they specifically chose the bound for that reason. So let's take that on faith, maybe. Alright, so we need to identify what the inside and outside functions are. This is a little tricky, and I'll give you a few seconds to think about it. Think you got an idea? If you're stuck, it's helpful here to rewrite it. When you see something in a denominator, that's a lot of times a good thing to do. Alright, so I pulled the dx out to the side. Then how could I rewrite the over x minus 5 part? That would be x minus 5 to the power of negative 1. Now do you see the inside and the outside functions? Yeah. Inside is x minus 5. And the outside is the to the power of negative 1. We have the chocolate and the candy shell again. Alright, so let's move forward with the anti-chain rule. We need the derivative of the inside. What's the derivative of x minus 5? Oh, that's 1. That's nice. So I'm dividing by 1. And nothing happens. Woo! Okay. So now I need the antiderivative of the outside. Okay, so how do I do an antiderivative of something to the power negative 1? Well, here's what a lot of people do that isn't right. Well, let's increase the power by 1 and then divide by the new power. Except you can't divide by 0. Don't do that. Okay, what do we do instead? Now, if it had been any other negative power, then I could have increased it by 1 and divided by the result and been just fine. But with a negative 1, it's something special. Remember, this is 1 over stuff. What function has a derivative that is 1 over stuff? Oh, that would be the natural log. Don't forget the absolute value bars. And we'll keep the inside the same. There we go. So, if I were to take the derivative of that just to check my work, derivative of natural log is 1 over stuff. Times derivative of stuff would be 1. Okay, that's it. Now, we're not done. We still got to work the bounds here. And now you might get an idea of why that e plus 5 is actually going to turn out to be helpful. If you think you can do it, pause the video and skip ahead and see if you get the right answer. Or stick around. Alright, so plug in the two bounds. We plug in e plus 5 in the first parentheses and 6 in the second. There's nice canceling out going on there. Natural log of e minus natural log of 1. Okay, natural log of e is 1. And natural log of 1 is 0. Hopefully you've learned those by now. If you haven't, you might want to memorize those. And 1 minus 0 is 1. Wow! Okay. So much for climactic effect. Okay, well, I'll see y'all in class.